Okay, so here we go with chapter 8.5, starter 1. There's only 2 starters with this little exercise because this first one is quite lengthy. So I want you to read through the question, or I'll read it through for you in a moment, but I want you to then come up with a plan, check that your plan is appropriate before then trying to do the question. Okay, so what we've got is set of connected particles, string is light and inextensible as usual. The coefficient of friction between A and the rough plane, so the plane is rough, is mu equal to 1/2. Assuming A does not reach B, find the distance A moves up the plane before coming to rest. So I want you to put the additional forces on the diagram that are currently missing. And then I want you to come up with a plan, and I will outline a plan in a moment, and then check that that plan's correct before you then proceed with the rest of the starter activity. Okay, so forces on, write down your plan and then check against this. So the additional forces we've got on here are the weight, 2G acting downwards. We've got a normal reaction, R, and we've got a friction opposing the motion up the plane. So they're the extra forces. Our plan, 1, use connected particles approach, so that's what we usually do when things are connected, to find acceleration of A and C. 2, we need the speed C hits ground using CVAT, or constant acceleration equations, because the acceleration is constant. We then need to 3, find the acceleration of A once C has hit ground, and then 4, distance moved by A in coming to rest. And probably the thing that I haven't highlighted in what I've written there is the speed that C hits the ground is the speed that A is travelling up the plane. And then when the string becomes slack, there's no longer acceleration up the plane, but the friction will act now. The friction will continue to act down the plane, slowing it down until it comes to rest. Okay, so now try to get the answer out from there, and then check against what follows. So, first phase is to probably find the friction acting on A. So, since sliding, friction is equal to mu R. Mu we know is 1/2. R we can get from resolving perpendicular to the plane on A, which is going to give us R minus 2G. I haven't given an angle in there. Let's call that 30 degrees. Okay, so 2G cos because it's next to the angle. So cos of 30 equals 0 since equilibrium. So R is equal to 2g. Cos of 30 is root 3 over 2. So it's root 3g. We substitute that. Into here for R, and we've got friction equals a half of, as mu, R, which is root 3g. So we've got root 3g over 2 for the friction. Okay, now let's think about our connected particles. We're going to apply N2 up the plane on A. Apply N2 parallel to the plane and up the plane on A. And we get T minus the friction, which is root 3 over 2g, minus the component of the weight. Now, I've done this lots now. It's opposite the angle, so that was 30 degrees. So this is going to be 2g opposite sine 30. So we get down here minus 2g sine of 30 is equal to m, which was 2a. Tidy that up. So we're going to get t minus root 3 over 2g. Sine of 30 is a half, so minus 2g over 2 is minus g equals 2a. Okay, apply N2 on C, and that's going to be downwards, so the acceleration continues in the same direction, in effect, of the motion of the connected particles. So we get, acting down, 5g minus t. 5g minus t is equal to its mass, which is 5a, times the acceleration a. If we now add the two, we get 5g minus root 3 over 2g minus g equals 7a. So we get 5g minus g is 4g minus root 3 over 2g all over 7 is equal to a. If we just tidy that up, we will get 8g minus root 3g over 14 equals the acceleration. Okay, so we've now done that first part of our plan. Yeah, we've got use connected particle approach to find the acceleration of A and C. So we've got that. So we now want to find the speed of C hitting the ground using SUVAT. So, part 2, constant acceleration, working downwards. We've got U is equal to 0, because I think we said it was released from rest or something like that, assuming A does not reach. Find this, A moves up the plane before. We've not actually said it's going to, oh yeah, up the plane before coming to rest. And so really in that question I should have said released from rest. Yeah. So there's not much I can do about that now, sorry. So constant acceleration, U equals 0, A equals 8g minus root 3g over 14. S is it's got to go a distance of 2 meters. And V is what we're trying to find. So we're going to use V squared equals U squared plus 2AS. So V squared equals 0 squared plus 2 times 2 the distance times the acceleration, which is 8g minus root 3g over 14. So V squared equals, the 2 cancels with the 14 to leave 7. So 2 lots of 8g minus root 3g over 7. So V is going to be equal to the square root of that. Okay, now third phase, so we've now got the speed of C when it hits the ground, and we've got to know the speed of C, the speed that C hits ground is the speed of A when the string becomes slack. Okay, so what do we now know? So we've now got a new acceleration because we've got our weight, 2g acting downwards. We've got our friction, which is unchanged because it's still sliding. Yeah, that's going to be unchanged since still sliding. It's a property of the contact, so it's not affected by the string or the tension, because the tension was horizontal. That's 2 kilograms. So we've got an acceleration acting down the plane now. So we apply N2 down the plane. So we've got the friction plus 2g sine, this angle was 30, so that's 30, and we're using this opposite bit, so this will be 2g sine of 30. So we've got 2 friction plus 2g sine 30. Anything else acting down the plane? No. So that equals m, which is 2a. 2g sine 30 is g. So friction plus g equals 2a. Friction is unchanged. So we've still got root 3g over 2 from here. Root 3g over 2. So root 3g over 2 plus g equals 2a. So a equals root 3 g over 4 plus g over 2. Or g over 4 times root 3 plus 2. Taking out the g over 4 as a factor, leaves root 3 plus 2. for the acceleration. Okay, so now we've got that acceleration down the slope. So if we now use constant acceleration, our initial speed is the speed we had at the end here. So it's the square root of 2 over 7 times 8g minus root 3g. So 2 over 7 g 8 minus root 3. I think we got that right. Yeah. Okay. V, well, we want how far it's travelled when it stops. So that's got to be 0. A, we have just worked out, but it's going to be negative because it's opposing the motion. So it's minus 8g over 4 root 3 plus 2. And S is what we're trying to find. So what equation should we use? V squared equals u squared plus 2as. Substitute in 0. U squared, well, that's straightforward. Just take off the square root sign. 2/7 g, 8 minus root 3 minus 2 times a, which is negative g over 4 times root 3 plus 2. Plus 2as. Oh, that's plus, sorry. Okay, now let's add that across. So we get g over 2 root 3 plus 2. Should have had an s on there. V squared equals u squared plus 2as is equal to 2/7 g 8 minus root 3. The g's cancel. So S equals 4 multiplied up by 2 over 7 times 8 minus root 3 times root 3 plus 2. Tidy it up. Let's rationalise the denominator. So we're going to multiply by root 3 minus 2. So we will have on the bottom, root 3 times root 3 is 3, minus 4, so that's going to be minus 7 on the bottom. And on the top, we're going to have 4 lots of well, we can use a grid. 8 root 3 plus 2 root 3 is 10 root 3 minus 3 minus 16 minus 19. So that's 4